Have you ever extended a class only to realize your new subclass breaks everything? It compiles fine, but when the system runs, it behaves unexpectedly. Just because a class inherits, it doesn't mean that it should substitute. Welcome to another video on object-oriented programming using C Sharp. And the topic for today is Liskov Substitution Principle, the most misunderstood rule in object-oriented programming. The formal definition of Liskov's substitution principle states that if S is a subtype of T, then objects of type T should be replaceable with objects of type S without breaking the functionality of your program. In simple terms, this means if a child class inherits from a parent class, you should be able to use the child class wherever the parent class is expected, without any surprises or failures. If there is any surprises or failures, that is a violation of Liskov's substitution principle. Now let's bring this concept to life with a visual on the left. Imagine you have a base class, Beverage dispenser. This class has a method called auto dispense. It represents the behavior of pressing a button and getting the drink of your choice. We then create 4 child classes from it: a coffee dispenser, a juice dispenser, soda dispenser, and the last is a tea bag dispenser. All good so far. Now, here's where things go wrong. The first 3 dispensers, coffee, juice, and soda, all work exactly as expected. You press the button and the drink is automatically dispensed. But when it comes to tea bag dispenser, we hit a problem. This one doesn't support auto dispensing at all. Instead of giving you tea, it throws an error. This dispenser does not support auto dispensing. This is equal to our not implemented exception when it comes to a code example. This violates LSP. Why? Because the tea bag dispenser is not a valid substitute for its parent class beverage dispenser. It breaks the contract. To fix this, we might need to rethink our hierarchy. Maybe we can have a base class auto dispensable beverage implemented only by classes that truly support auto dispensing. We can have a separate base class for dispensers which don't support auto dispensing. This ensures that only compatible types share the same behavior, preserving substitutability and respecting LSP. Now let's understand this better with a real world example. Whether you're flying economy, business, or first class, one thing remains the same: your ticket guarantees you a seat on the flight. But what if one type of ticket doesn't fulfill that promise? Let's explore how it connects to Liskov substitution principle. Here we have 4 types of flight tickets: economy, business, first class, and standby. Now imagine all 4 ticket types are subclasses of a base class called flight ticket. This base class defines one critical method: assign seat. Because any valid ticket should be able to assign you a seat on the flight. Economy, business, and first class all support assign seat. They guarantee you a confirmed seat. But standby is an odd one out. It represents uncertainty. You might get a seat or you might not. So what happens if your application blindly treats every flight ticket the same and tries to assign seat for all of them, including standby? The standby ticket throws an error: seat assignment unavailability until gate confirmation. This breaks the Liskov substitution principle. According to LSP, if S is a subtype of T, then object of type T should be replaceable with object of type S without breaking the functionality of your program. In this analogy, we can't treat standby ticket as a true subtype of flight ticket because it doesn't honor the behavior expected by the base class. It can't safely replace it. It can't substitute it. Now let us look at this violation of Liskov's substitution principle in the form of code to understand it better, and then we will look at a code which applies Liskov's substitution principle to solve the problem. We start with a base class called flight ticket. It has a virtual method named assign seat. This method assumes that any type of ticket can be used to assign a seat. We then create three derived classes: economy, business, and first class ticket. All of them inherit from flight ticket, and they don't need to change any behavior. So, when you call assign seat of any of these, it works exactly as expected. These are good citizens of Liskov substitution principle. They can safely substitute the base class. But then we introduce standby ticket. This subclass also inherits from flight ticket, but there is a twist. It cannot guarantee the substitution. So instead of assigning a seat, it throws an exception. This is where things start to go wrong. Let's look at the main method where all tickets are processed. What's the intent here? We are treating all ticket types as if they follow the same rule, that calling assign seat will always work. But as soon as standby ticket is included, your application crashes with an invalid operation exception. This violates Liskov substitution principle, which says you should be able to substitute any subclass for its base class without breaking the program's behavior. But standby ticket breaks that promise. It changes the behavior of the base class in a way that makes it unsafe to use interchangeably. The design forces you to write defensive code. This type of design forces developers to write defensive code, like introducing a if statement to check whether it is a standby type of ticket, and then calling ticket.assignSeat. And now you're doing manual checks, which defeats the whole point of polymorphism and clean object-oriented programming design. So what's the fix? We will look at this in the next example, in which we apply Liskov substitution principle. In our previous example, we saw how standby ticket class couldn't substitute its base class and how it violated Liskov substitution principle by throwing an exception. Now let's look at how to properly apply Liskov substitution principle by redesigning our class structure to make it clean, safe, and extendable. Let me remind what LSP says. Subtypes must be substitutable to their base types without altering the correctness of the program. In our earlier code, standby ticket inherited from flight ticket but failed to uphold this contract, specifically the assign seat method, which led to runtime exception. Let's fix that. Instead of forcing all ticket types to share the same assign seat behavior, we have now introduced an interface called iSeatAssignable. Only ticket types that actually support seat assignment will implement this interface. This gives us a clean separation of responsibility. We no longer assume that all flight tickets behave the same. Let's model our real-world ticket types: economy ticket, business ticket, and first class ticket. All implement iSeatAssignable interface, so they provide their own implementation for assign seat. Standby ticket doesn't implement this interface. Instead, it has its own method called wait for confirmation, which reflects the real life behavior. Now, let's look at how this helps us to write better, cleaner client code. No more runtime crashes, no more unpredictable behavior. We are checking the behavioral capacity of the object, not making assumptions. This version now fully complies with Liskov's substitution principle. All substitutable types, economy, business, and first class, can be safely used in place of iSeat assignable contract. Standby ticket no longer pretends to be something it's not. It doesn't pretend to substitute a base class that it cannot substitute, and it is modeled correctly. This is the essence of Liskov's substitution principle in real-world design. Inherit a class only if you can completely substitute it. If your subclass doesn't fully support the behavior of its parent, Don't force it to fit. Design it separately with its own responsibilities. Now that we understand what Liskov's substitution principle is and how to apply it, let's talk about why it actually matters. Here are the real world benefits you get by following LSP in your code base. It enables true polymorphism. You can safely use any derived class wherever the base class is expected without worrying about special cases or unexpected behavior. That's the foundation of solid object oriented programming. It prevents runtime errors. When your subclasses honor the contract of their base classes, you avoid those unexpected exception moments like method throwing not implemented exception or breaking the logic flow. It promotes interface segregation when you realize that not every child class should inherit every behavior. You start thinking in terms of capabilities instead of one size fits all inheritance. This often leads to better design through smaller and more focused interfaces. It enables safer unit testing. Tests written for the base class will naturally pass for any subclass that respects LSP. That means you don't need to write defensive or duplicated tests. It improves code readability and intent. When someone reads your class hierarchy, they can understand the behavior. No hidden if else logic, no mental gymnastics, just clarity. It supports open close principle. You can add new subclasses without modifying existing code because everything just works as expected. This makes your system more scalable, maintainable, and extensible. By following the Liskov substitution principle, you don't just make your code correct, you make it cleaner, safer, and ready for a long term growth. Thank you for watching our video and do subscribe our channel for more such videos, and thank you very much for your support.